In this video, we're going to talk about the maximum rate of increase of a function. And this is going to involve a discussion about the gradient. So hopefully you've already watched the video on the gradient. So here are a couple of facts. After we state them, we'll talk about why they're true, and we'll do an example as well. So first fact is that the gradient of f points in the direction of the maximum rate of increase of f. Okay, so this is a little bit wordy here. If you just picture this geometrically, imagine that f is represented as a surface, for example. You could even imagine it physically. Let's say that surface is a mountain or something that you're trying to climb. So at any point, if you look around you and figure out what the steepest direction is, maybe it's up this way, the gradient of f is what's signaling that direction. So the gradient of f points in the steepest direction. Second fact is that if you wanted to know what that maximum rate of increase of your function is, the way that you get that numerically is you just calculate the length of the gradient. So let's talk briefly about both these points, understand why they're true, and then we'll do an example. So point one really has to do with the directional derivative. So we know our formula for the directional derivative. We can take the gradient, dot it with the unit vector u that represents the direction. And let's think back to linear algebra and remember the formula for the dot product. So if you're taking the dot product of two vectors, you're supposed to take the length of those vectors, multiply the lengths together, and then you multiply that by cos theta, where theta is the angle between your two vectors. So suppose your gradient vector pointing like this, and let's say u going like that. So theta would be the angle between those two vectors. So cos theta is taking on some value between -1 and 1. So this whole quantity here is going to be maximized when cos theta equals 1. That's going to happen when your two vectors are pointing in the same direction. In other words, when the angle equals 0. That's when this quantity is going to be maximized. So let's say it's maximized when vector u is parallel to the gradient of f. So if we ask in what direction are we going to experience the maximum rate of increase of f, well, vector u is that direction. In what direction is u supposed to be pointing? Well, gradient of f. Okay, let's briefly try to understand fact 2. So if we wanted to actually calculate the maximum rate of increase of f, we need to know in which direction u is supposed to be pointing. So from part A, let's say, suppose that vector u is parallel to gradient of f. That's when we're going to experience the maximum rate of increase. And since u is a unit vector, that means u is going to be the gradient of f just divided by its length. Okay, so that's the special direction in which we are going to experience the maximum rate of increase of f. So if we then wanted to calculate the rate of increase of f, we would do our directional derivative. So we're going to take our gradient, dot it with our vector u. And we've already decided that in this situation where we're going to experience the maximum rate of increase, u had better be the gradient of f divided by its length. Okay, so when you dot a vector with itself, you get the square of the length of that vector. So we've got length squared of the gradient of f, and that's divided by the length of the gradient of f. So one of these factors of length is going to cancel out, and we'll just have length of gradient of f. So that is establishing fact 2, which says the maximum rate of increase that you can get is the length of the gradient. And that would only happen if you were headed in that special steepest direction. So here we have a function of x, y, and z measuring temperature in degrees Celsius at any point in space. And we've got a point P, which is a point that we specifically care about in this problem. The position x, y, and z are going to be measured in meters. All right, so starting from point P, in which direction does f increase fastest? In other words, if you were standing at P, in which direction would you experience the fastest rate of temperature increase? So to do this, we're going to just calculate the gradient, because that's going to give us the direction of the maximum rate of increase of f. Since our function involves 3 variables, our gradient's going to have 3 components. So partial with respect to x, 3x squared, partial with respect to y, 2y, and partial with respect to z, 4. Since we want to evaluate this since we're interested in point P, we're going to evaluate this at point P. So you could just write something like gradient of f at P is good notation here. And so subbing in the values x, y, z equal 1, 2, 3. All right, so doing that, we're going to get 3, 4, 4. And so if you travel in the direction of this vector, 3, 4, 4, from P, that's the direction in which our temperature function is going to increase fastest. Now, if we want to figure out what is the actual maximum rate of increase of F, so we want to talk about in terms of degrees Celsius per meter, how fast can we make that temperature increase? To do that, we would just calculate the length of the vector that we found above, the length of the gradient vector. So if it's point P that you're interested in, you're talking about the length of the gradient vector when it was evaluated at point P. Okay, so it's just a matter of taking the length of this vector 3, 4, 4 that we calculated above. So for the length, take the square root of each of the components squared and summed up. So that gives us a nice root 41. And since that's a rate of change of f, the units are going to be the units of f divided by the units of whatever your x, y, and z are measured in. In this case, it was meters. So degrees Celsius per meter, that's the fastest rate at which f can be increasing. So that's all about maximum rate of increase and how the gradient can be useful to us. Thanks for watching.